Welcome back to MathMuni. Today's practical problem focuses on a story inspired from the Ramayana, the ancient Indian epic. The specific situation here involves a demon, Maricha, who is disguised as a black deer making an escape. A noble prince is on a chariot trying to hunt down Maricha. Now we have a wonderful poem that describes the chase in detail. The poetry is very interesting, but our job here is to pick out the relevant information from all of the details given in the poem that helps the noble prince get the job done. The first thing to note in the very first paragraph is that the black deer Maricha is moving southwards. The second paragraph suggests that there is a road perpendicular to the track followed by the deer. And in the third paragraph, we learn that the noble prince is on his chariot, moving eastwards on this perpendicular road. And then there comes an instant when both the hunter and the prey, the prince and the deer, see each other. At that instant, their line of sight makes an angle of 45 degrees with the direction of the two roads. At that instant, the noble prince on his chariot shoots his arrow. And the question in front of us is at what angle should this arrow be aimed so that it gets to Maricha? Now clearly, that angle is not 45 degrees. Why is that? Well, simply because all three participants in this story, the deer, the noble prince on his chariot, and the arrow are in motion at different velocities and in different directions. The direction of the arrow is the unknown piece of the puzzle that makes the whole thing fit. We also have some data. Maricha, the black deer, is moving south at 20 miles per hour. The noble prince is moving east at 50 miles per hour. And the arrow, once it leaves the bow, will have a velocity of 1000 feet per second. And assume that all three velocities are constant, so there is no acceleration or deceleration involved. So we have different things moving around in different directions, and the job in front of us is to determine when and how two of those things, the deer and the arrow, will meet. This problem is a perfect fit for using vectors. A vector, as you know, has a magnitude and a direction. Every one of the velocities in this problem can be seen as a vector. So let's put these vectors to work to answer our question, which is, what is the direction of the arrow? Okay, first things first. We start by drawing a figure. The chariot is moving east and the deer is going south. Chariot is moving at a speed of 50 miles per hour from west to east, and the deer is moving from north to south at a velocity of 20 miles per hour. At some instant, the line of sight joining them makes an angle of 45 degrees with the two perpendicular lines. Now we don't know exactly what that point on the road is, so let's assume some point, say minus A0 on the east-west road and 0A on the north-south road. At that instant, the line joining the chariot and the deer makes an angle of 45 degrees. Now we don't know the value of A, but let's not worry about it now. We will tackle it later. And what about that other unknown, the arrow? For now, let's assume that it is aimed at an angle of alpha with the horizontal with a velocity u. Now we don't know alpha. Our goal is to find alpha. But we do know what u is. It's the velocity of the arrow, which is given to us as 1000 feet per second. We will use it at the right time later. So in vector notation, we could say that the vector of the deer's velocity is 0 minus 20. The first number 0 is the movement in the x direction, which is 0 because the deer is going south. And the second number is minus 20 because, well, it's going south or in the direction of the negative y-axis. Similarly, the vector for the chariot is 50, 0 because it is going east or in the positive direction of the x-axis and has 0 movement in the y direction. Now here comes the interesting part, and it relates to the arrow fired from the chariot in the problem. Or in modern times, I guess one might imagine that it is a bullet fired from a train. The velocity of the bullet relative to the train, or in this case, the velocity of the arrow relative to the chariot, is u cos alpha in the x direction and u sin alpha in the y direction. And we get this just from the resolution of the velocity u into the x and y directions respectively. Now here comes the most crucial part of the problem. After this, it's just the mechanics. This velocity of the arrow relative to the chariot is simply the absolute velocity vector of the arrow minus the absolute velocity vector of the chariot. And why is that? To understand that, let's actually take a little detour to a simpler one-dimensional example that we can understand intuitively. Assume that you are in a train that is moving at 100 miles per hour. From this train, a man throws a stone with a velocity of 20 miles per hour in the direction of the train. Now, if the train were at rest, the absolute velocity of the stone would be 20 miles per hour. But actually, the train is moving, so the velocity of the stone relative to the train is 20 miles per hour, but the actual velocity of the stone is 100 plus 20, or 120 miles per hour, benefiting from both the velocity of the train and the velocity the man gives on top of it in the same direction. So we can intuit this easily in one dimension. No mathematical tools are needed. But when you move into 2 or higher dimensions, it is so much easier to formalize our thinking. And that is where vectors come in handy. In this example, we will say that the relative velocity of the stone is equal to the actual velocity of the stone minus the actual velocity of the train from which it was thrown. Now let's go back to our original deer and arrow problem. We have the relative velocity vector of the arrow vector relative to the chariot, or the arrow vector minus the chariot vector. So the actual velocity of the arrow is equal to the velocity of the arrow relative to the chariot plus the velocity of the chariot. We have all of this in the notation that breaks apart the x and y directions derived above. So the velocity of the arrow is equal to u cos alpha, u sin alpha plus 50, 0, which is equal to 50 plus u cos alpha, u sin alpha. So we now know the vectors for the arrow and the deer. Remember, we also have their starting positions, 0a for the deer and minus a0 for the arrow. So now it becomes simple to say where the deer and the arrow will be after some arbitrary time t. The position of the deer after time t is equal to the starting position 0a plus the deer's velocity vector 0 minus 20 times t. This is equal to 0 in the x direction and a minus 20t in the y direction. Similarly, the position of the arrow after time t is equal to the starting position minus a0 plus the arrow's absolute or actual velocity vector calculated above, which is 50 plus u cos alpha and u sin alpha in the y direction multiplied by t. And this comes to minus a plus 50t plus ut cos alpha in the x direction and u sin alpha times t in the y direction. The deer and the arrow will meet when their coordinates are the same. To be precise, when both their x coordinates and y coordinates are exactly the same. And that will happen at some value of t. and some selection of the angle alpha. In other words, 0 a minus 20t from the position of the deer is equal to minus a plus 50t plus ut cos alpha and u sin alpha times t for the arrow. So we equate the x coordinates and we equate the y coordinates, and we have two equations with two unknowns. The two unknowns are t and alpha. Therefore, 0 is equal to minus a plus 50t plus ut cos alpha from the x direction, and a minus 20t is equal to ut sin alpha from the y direction. The first equation implies that t times in brackets 50 plus u cos alpha is equal to a. And the second equation implies that t times 20 plus u sin alpha is equal to a. These two equations give us the value of a upon t, which is equal to 50 plus u cos alpha from the first equation is equal to 20 plus u sin alpha from the second equation. This implies that u times in brackets sin alpha minus cos alpha is equal to 30, which implies that sin alpha minus cos alpha is equal to 30 upon u. Remember that we know the value of u, so we know the right hand side. Now this is a fairly standard trigonometric equation which can be solved by multiplying both the left hand side and the right hand side by 1 upon root 2. The left hand side can be written as sin alpha multiplied by cosine of pi by 4 minus cosine of alpha times sine of pi upon 4. And this is equal to 30 divided by u root 2 on the right hand side. Notice that the left hand side can be written as sine of alpha minus pi upon 4. And this is equal to 30 upon u root 2. Now we are given that the value of u is equal to 1000 feet per second. We need to convert this into miles per hour to be consistent with the rest of the problem. We divide the 1000 by 5280 to convert the feet into miles, and multiply by 3600 to convert the seconds into hours. This gives us the answer in miles per hour. And this simplifies to 15,000 divided by 22 in miles per hour. Substituting this value of u in the trigonometric equation just derived, we get sine of alpha minus pi upon 4 is equal to 30 divided by root 2 multiplied by 22 divided by 15,000 from the result just obtained for the value of u. In other words, alpha is equal to pi upon 4 plus sine inverse 11 root 2 divided by 500. And this comes out to approximately 46.8 degrees. So we have our answer for the direction in which the arrow needs to be aimed. But one thing might puzzle you. The deer is running south, so clearly the arrow must meet it on the y-axis south of the 45-degree line. But our calculation tells us that alpha is 46.8 degrees, which means that the arrow is aimed above the 45-degree line. That sounds like a contradiction, or did we make a mistake somewhere? To resolve this, first we check that even with the current answer, if we aim the arrow above the 45-degree line, where exactly does it cross the y-axis and meet the deer? Remember from the equations calculated above that y is equal to ut sin alpha and t is equal to a upon 20 plus u sin alpha. Combining these two equations, we get y is equal to u sine alpha divided by 20 plus u sine alpha times a. Notice that 20 plus u sine alpha is greater than u sine alpha. In other words, the denominator is greater than the numerator. Therefore, this fraction is always less than 1. And therefore, the value of y, meaning the point on the y-axis where the arrow meets the deer, is less than a. Therefore, the arrow hits the deer below 0a, even though it was aimed above the 45-degree line with an alpha of 46.8 degrees. And this is because of the additional horizontal velocity. Imparted to the arrow by the horizontal velocity of the chariot. So, finally, what did we learn? Well, to start with, please draw the figure. It'll clear up a lot of things. Don't try to do everything in the head. I've been telling my kids since they were in kindergarten, and now they are in university. Then in this case, recognize that it is a problem that lends itself well to the use of vectors. Each of the three players in the story, the deer, the chariot, and the arrow, have a velocity vector associated with them. Some vectors are given in absolute terms, but some are given in relative terms. In this case, we were given the relative velocity of the arrow, and we found it useful to convert it into absolute or actual velocity of the arrow. Combining the vectors with the starting positions, we were able to find their positions after time t. By the way, we did not really know the precise starting positions, but we assumed something, and it turned out that we were able to eliminate that parameter a from the equations through a little arithmetic jugglery. And then we equated the positions of the deer and the arrow to find the time t when they met and the corresponding angle alpha. And finally, we noted that the arrow was aimed above the 45-degree line, but ended up meeting the deer on the north-south line below the 45-degree line. This made sense because of the additional horizontal velocity imparted to the arrow because of the movement of the chariot. So that's it. We have it all figured out. Maricha is cornered. You see how, through the right use of mathematics, in this case through the use of vectors, we were able to cut through the fog of the hunting problem and get to a practical and precise answer. And that is why mastering mathematics is so important. I hope you had fun, and I will see you back at MathMuni for the next story, where mathematics comes to our rescue and saves the day. Meanwhile, check out mathmuni.com for hundreds of mathematical problems across a range of topics. We are rapidly expanding our collection and would love to hear your feedback. Please drop your suggestions in the comments below. Bye for now.